Okay, so this is going to be the first lecture on multivariable calculus, and in the first lecture we will be starting with the concept of functions of several variable functions. Okay, so previously we have already studied functions of single variable where we had a domain D. We used to map elements of D to some element R, right? Elements of this set R, which obeyed some conditions. Let's say fx equals to y, right? So we used to map elements of x to elements of y, where y was called the image of x and x was called the pre-image of y. The condition for f to be a function which is mapping elements from D to R is that every element of x, every element of D must have a unique image in R. Okay, that is there exists y belong to R for all x belongs to D such that fx equals to D and and x1 equals to x2 implies fx1 equals to fx2. Clear? This was the condition we had. Got it? So this basically implies that the function is well defined. So in a similar way, we domain and range, domain, codomain concepts of single variable functions are already done. So I'm not gonna focus on those particular topics. In exactly a similar way, we define what we call a two variable function, or let's say a three variable function, or let's say a multivariable function. Okay. Okay, I'm just giving you a little bit summary of what is domain, codomain, range of single variable functions. So when we had a mapping from D to R, this D, that is the elements which are getting mapped, the set of those elements were called the domain of the function, and R is called the codomain of the function. Okay, R is the set of those elements which are the images of the elements of D. Okay, it is not mandatory for all elements in R to be images of the elements in D. Okay, what am I trying to say is that, see, we have fx equals to y for all x belongs to D, but the set of fx, that is the set of all the images of the elements of D, is basically contained into contained in equal to R. Okay, so this is a subset of R. It might be equal to R, but it is not mandatory to be equal to R. Okay, but this set, which is the set of all images of the elements of D, this set is called the range of the function, range of f. Okay, so these are the basic definitions of functions: domain, codomain, uh, domain, codomain, range. Okay, then we had also discussed about the types of functions. We have into function, onto function, bijective function, many to one function. Okay, and previously we have also learned how to find the domain of a function. So what is basically finding the domain of a function? So suppose you are given a function like this, so we need to just find out the set of elements which can be used as an input to this function. As simple as that. Okay, for example, see, if this is the function you have. Okay, now see, root over of x square minus 1 is the provided mapping, or the provided rule for this mapping to exist. Okay, now we know that x square minus 1 can be, or rather let us say it like this, that we can use x as an input to this mapping if x square minus 1 is greater than equal to 0, because if x square minus 1 is less than equal to 0, then this becomes an imaginary, a complex number, an imaginary number. It no more remains a real number. But in case of functions, and we are taking these functions to be real functions, for that reason we cannot take complex functions into consideration. Rather, we must always take the domain to be something real. Okay, that is why we need to take x square minus 1 is always greater than equal to 0. So from here we get a particular set, that is x is either greater than equals to 1 or x is less than equals to minus 1. That is, we can get a set like this, that you have minus infinity to minus 1 union 1 to infinity. So this becomes the domain of the function where the rule is fx equals to root over of x square minus 1. This is basically what, how to find domain of the functions. And then let us stick to our point, that is, what is a multivariable function. So its definition is almost same as that what we had studied in case of single variable function. So suppose you have two real sets. Okay, you have one real set x and you have one real set y. Okay, real set means these sets are the subsets of the set of real numbers. Now if for all xy, which is an ordered pair, that is an element of the Cartesian product x cross y, there exists a unique real number z according to some given rule f of xy, then f of xy is called a real valued function of the two variables x and y, and is given as z equals to f of xy, where small x is the element of capital X and small y is the element of capital Y. Okay, and here x and y are independent variables while z is a dependent variable. When you had a function y is equals to fx, here x was called the independent variable and y was called the dependent variable. Reason being key, x is used as an input and it can be any value provided by u. Okay, providing a value to the function as an input is not depending on anything, while y is being dependent on the values entered as input, right? That's why x was called the independent variable and y was called the dependent variable. What is a multivariable function is that you take a real set r, I mean you take a real set x and you take a real set y. Okay, you form its Cartesian product, that is the set of all ordered pairs xy, where small x is an element of capital X and small y is an element of capital Y. Is it clear? Now you take a mapping from x cross y to some set, let's say z. Okay. So it says that for all xy, that is an ordered pair belonging to the domain of the function. Now this becomes the domain of the function, right? There exists a unique element of capital Z such that f of xy equals to z. The same definition as we used in a single variable function. The only difference is that here you have two independent variables x and y. Clear? Got it? In extremely similar way, we can form a n variable function. N variable function means you have n independent variables. Suppose you take a subset of the nth space of R. Okay, R to the power n. This symbol means cross product of R n times. Okay, so the elements of Rn is basically of the form a1, a2, a3 and so on till an, where each ai belongs to R for all I belonging to the set 1 to n. Okay, that means T will be of the similar fashion. T will also contain elements of the same form a1, a2, a3 till an, right, for all ai belonging to R such that 1 less than equals to I less than equals to n. Okay. So if you take a function, a set T of this form, and you assign a rule f on T such that f takes all these elements to some value w, okay, which may also be a real number itself, then you are having n independent variables and one dependent variable, and such a function will obviously give you what you call a n variable function. Let's say for example, you take f from T to R such that x1 square plus x2 square and so on till xn square equals to z. So this gives you a multivariable function and an n variable function. Here you have n independent variables which all together are getting mapped to something called z. Okay, this is the basic. So now let's come back to our concept of two variable functions. So the first thing is how to find the domain of a two variable function. Now the process to find domain of a two variable function is exactly same of what we did in the single variable function. Okay, suppose you are given a function f xy of the form root over of x square plus y square. Now since this is a real valued function, that means root over of x square plus y square must be a real number, which implies x square plus y square must be greater than equals to 0. So this is the domain of your function. And we know that, see, now we know x square plus y square are greater than equal to 0 for all xy belonging to R cross R, that is basically R square. So we can say that the domain of the function is simply R square, as simple as that. What is the range of the function? Since x square plus y square is always positive, so its root is also always positive. So the range of the function is from 0 to infinity. Okay, what we did in single variable function, the basics of that is always same in case of multivariable function. It's just some concepts differ in terms of the independent variable. Clear? For example, if this is a function root over of x minus y square, So to find the domain of the function, we need to take x minus y squared to be greater than equals to 0, because you have f as a real valued function. So this region is the domain of the function. Clear? If you have f of x, y, z is equals to 1 over x square plus y square plus z square, you need to find the domain of the function too. So for this function to exist, x square plus y square plus z square must not be equals to 0. And we know x square plus y square plus z square must not be equal to 0 implies that x, y, and z individually are not equal to 0, because that is the only condition for their sum, for the square of the sum of the squares to be 0, right? So we can take the domain of the function to be, you know, Cartesian product of r 3 times, that is r cube, except the element 0 comma 0 comma 0. Clear? So this is what we have in as a domain and range in multivariable functions. You can check on your own some further problems. For example, if your function y z ln x, now see the domain, to find the domain of the function, we need to check for what values, for what inputs x, y, and z you have f as a real value. You get y z ln x as a real value. Now y and z might be anything, any real number to get this a real value. But what problem appears is that you have logarithm of x, and we already know that if x is less than equals to 0, logarithm of x does not exist, right? So the domain of the function must be set of all those values of x which are greater than 0, because domain of this function is not at all depending on y and z, right? So the domain of the function is x greater than 0, the set of all elements x belonging to real numbers which are greater than 0. And since this domain is depending only on one of the variables out of the other variables present, we define this domain as a half space. Okay, we define this domain as a half space. Got it? What range is a real number? Clear? So this is basically the concept of domain and range of a two variable function or a three variable function. Now let us come to the concept of interior point. What is the interior point? So a point x0 y0 in a region x, or you are given a region x and you take a point x0 y0, and since you can you always see that since this is an ordered pair, so this point must belong to the xy plane, obviously. Okay, so a point x0 y0 in a region s in the xy plane is called an interior point of s if there exists a disk centered at x0 y0 that lies entirely in s. Okay, what do I mean by this statement? See, so suppose you have the xy plane. Okay, suppose you have the xy plane and you take a region s. So this is a region you have s. Clear? Now you take a point x0 y0. So suppose you take a point here as x0 y0. Clear? Now if there exists a disk centered at x0 y0 that lies entirely in s, you can obviously see that you can form a disk centered at x0 y0 like this, and this disk is completely contained in this region s. Therefore you can say that x0 y0 is an interior point to the region s. Is it clear? Is it clear? What is a boundary point? So boundary point of a region s is x0 y0 if a disk centered at x0 y0, if a disk centered at x0 y0 contains points that lie outside of s as well as inside of s. That is, suppose you again take a region s and you take a point, let's say, Acha, this boundary of s is defined. Okay, this boundary of s is defined. What do I mean by the boundary being defined? I will tell you later. For at this moment, just just imagine that this boundary of s exists in this space. This, suppose this is a disk, proper disk which we have in real life. Okay, or let us just consider this s is basically a circle plus region inside the circle. Region inside the circle. Okay, so since this is a circle plus region inside the circle, so this is basically the circumference of the circle which exists in the real plane. Got it? Now if you take a point on the circumference of the circle, if you take a point on the circumference of the circle and you form a disk centered at this point, then you can obviously notice that this disk contains elements inside the region S as well as contains elements outside the region S. So this point forms a boundary point. Is it clear? Now let us check a few examples to understand that why did I use the term that the boundary of this of this region is defined. Let us see. Now see. So this is the first example. Okay. So you have a region xy belonging to R square where x square plus y square is less than 1. That is, you have a circular region. You have a circular region, but the circumference of this region is not existing. Is it clear? You have a circular region, but the circumference of this region is not existing. Because, see, if you form a circle and you take also this region into consideration, then every point of the circle, every point inside this region will satisfy the condition x square plus y square is less than 1. Suppose this region is, or this circle is of unit radius. Okay, so every point inside the circle will satisfy the condition x square plus y square is less than 1, and every point on the circumference of the circle will satisfy the condition x square plus y square equals to 1, because on the circumference of the circle means it lies on the circle. And lies on the circle means it satisfies the equation of the circle. And a circle of unit radius will have this equation x square plus y square equals to 1, provided the center is at the origin. We are taking the center at the origin itself. Okay, provided the center of this region is at the origin. But since you are given that the region is contained of the points x and y such that x square plus y square less than 1, that means the points which lie on the circumference of the circle are not existing. That means the boundary of this circle is not existing. Clear? Since the boundary of this point is not existing, now what will happen? Let's see. Now see, in this region we can take any point into consideration and we can form at least a disk centered at that particular point, which will be completely contained in this region. So we can find infinitely many interior points inside this region. But since the boundary of this particular region is not existing, we cannot take a point on the so-called boundary of the region as in the diagram, and we tell this to be a boundary point, because this boundary is not even existing, right? So this point, which is so called to be on the boundary of this region, is not existing. Got it? We can take infinitely many points inside the particular region, but there cannot be any point on the boundary of this particular region, because the boundary of the circle is not at all existing. Is it clear, guys? What I'm trying to say, is it clear? Okay. Now similarly, we take S as all those points which satisfy this equation x square plus y square equals to 1. That means we simply take a circle and set off all those points which lie on the circle. Okay, if that particular thing happens, then it's just you have a boundary defined, but there is no region defined here. Okay, you cannot find anything inside the circle or outside the circle, because you can take only points on the circumference of the circle. So this is not basically giving you a region. So this example you cannot consider in the concepts of interior point and boundary point. But if you take a region, I think I have taken the example below. Okay, I'm giving you here itself. But suppose if you take a condition, or if you take a region xy belonging to R square, such that x square plus y square is less than equals to 1. Now see what happens. So you take the xy plane, you form a circle around the origin. Okay. Now in this case, the boundary is defined by the circle x square plus y square equals to 1. And you can take any point from inside the circle, because that region is also defined here. Now if you take any point from inside the circle, you can form a disk centered at that particular point, and you can see that the point is an interior point. You can also choose a point from the circumference of the circle which will satisfy the condition of the boundary point. So this particular region has both interior point as well as boundary point. So is it clear what are the concepts of when boundary point will exist, when interior point will exist? Because in this particular case, you cannot say that a point from here is an interior point, because a point if you take from here, and if you form a disk surrounded by centered at that particular point, that disk will contain no point of this region. The disk will contain no point of this region, because this particular region contains only those points which lie on the circumference of the circle. Is it clear, guys? Okay, let us come to the next statement. So here we define what is called an open region and what is called a closed region. Okay, so region is open if it consists entirely of its interior points. A region is open if it consists entirely of its interior points, and a region is called closed if it contains all its boundary points. Clear? So let's see. Now the first example which we did, if we take that particular region into consideration, let's say this region. Okay. Now in this particular region, you can choose any point from the region and you can form a disk centered at that particular point, and you will find that the disk will contain elements from inside the region. That is, the disk will be completely contained in the region, hence that point will be an interior point. And any point within from this region will satisfy the condition of the interior point. So you can always say that this region is an open region. This region is an open region. Also, this region has no boundary point because the boundary of this region is not at all defined. What can we talk about this region? This is basically not a region itself because it is just a set of those elements which lie on the circumference of a circle of unit radius. Clear? But we can say that this region basically gives you the boundary of the unit disk. This is called a unit disk. This is called a unit disk. Okay, this is called a unit disk. So the boundary of the disk was not defined. So we take a circle of unit radius and we can obviously see that this gives you the boundary of the unit disk. Now, if you take this particular region, which has the boundary of the unit disk as well as the region of the unit disk, then what we can have is that this region contains all its interior points, which is already given from here. Also, every boundary point of this region is contained in it. Every boundary point is basically all the points on the circumference of the circle. All the points on the circumference of the circle, x square plus y square equal to 1. Okay, and those can only be the boundary points because if you take a point even from slightly outside the circle, you can always form the smallest disk which lies entirely outside the region. Or if you take a point, let's say inside the circle but very close to the boundary, then also you can form a very small disk which lies completely inside the region. So the only possibility for a point to boundary point is that if it lies on the circumference of the circle, because if it lies on the circumference of the circle, you can form a very small disk, but that too will contain elements from outside the region as well as from inside the region. And every point on the circumference is contained in this region. That means all the boundary points is contained in the region. Hence, this particular region is called a closed unit disk, or a closed region rather. Clear? Clear? Let's come to the concept of what is a bounded region and what is an unbounded region. A region in the plane is bounded if it lies inside the disk of fixed radius. Otherwise, we call it an unbounded region. Is it clear? Is it clear? I will be explaining it. For example, say you take an XY plane and you form a rectangle. Okay, this is a region. This is a region. So this region is given by x equals to a and y equals to b. This is a region, let's say. Or let us say, let us define this particular region properly. Let's say you have this as x equals to a, this as x equals to b, this as y equals to c, and this as y equals to d. So this is a basically a rectangular region. Is it clear? Is it clear? Now for this particular region, you can always form a disk of fixed radius which will completely contain this region. You can always form a disk of fixed radius which will always contain this particular region. So this becomes a bounded region. So this becomes a bounded region. Clear? Lines can never be a bounded region. Lines can never be a bounded region, or half planes can never be a bounded region. For example, let's say, okay, you take a region between x-axis and the line y equals to x. Okay. Now, for this particular region, you can never form a disk of fixed radius which will completely contain this region. See, if you form a disk of this size, these parts will be not contained in the disk. You can form a hugely, you can form a as much as a large disk you can, but still it will not contain this region in itself, right? So lines, half planes, these are not bounded regions. These are unbounded regions. Clear? Clear? Next, we come to what we call contour lines. Okay. Let us first take the definition. So a plane z equals to c cuts a surface z equals to f of xy in the points given by f of xy equals to c. Okay, this curve, this curve is called the contour line of fxy equals to c. Okay, let's see here. So you have a curve z equals to 75 minus x square minus y square, right? So this is the curve z equals to 75 minus x square minus y square, and you take a plane z equals to 50, and you take a plane z equals to 50. So this curve and this particular plane, this curve and this particular plane cuts to form this particular circle by the equation x square plus y square equals to 25. So this becomes your contour line. This becomes your contour line. And if you just take the reflection of this particular contour line on the origin of the on the origin of this particular of this particular space, then that becomes the level curve of the function. That becomes the level curve of the function. Clear? See, take by an example. Let's say, see here, z equals to 50 on the surface of z equals to 75 minus x square minus y square is the given curve given. So contour line is basically the the intersecting curve formed by this particular line and this particular plane. Okay, and if you take that on the origin, okay, so this gives you the level curve. Okay, basically the further definition of level surface will give you the collection of all points x y z in space, but a function of three independent variables has a constant value f x y z equals to c is called the level surface of function. Let us take it by an example. So you are asked that for the level curve of the function f x y is equal to 16 minus, find the level curve of the function, find the level curve of the function f x y equals to 16 minus x square minus y square that passes through this point. Okay, so you are given the function f x y equals to 16 minus x square minus y square. If you put this value in the function, 2 root 2 times 2, you get 6. Okay, putting the value 6 here, you get x square plus y square equals to 10. So this gives you the level curve of the function. Is it clear? Very simple. Okay, now we come to what we call the limits of the multivariable calculus. We have already defined what is limit of a single variable calculus. Let us define it once more. So limit x tends to a fx equals to l. This means that for all epsilon greater than 0, there exists a delta greater than 0 such that mod of x minus delta, sorry, mod of x minus a less than delta implies mod of fx minus l is less than epsilon. Okay, that is the distance as the distance between uh, as the distance between x and a decreases or comes within delta. Basically what happens here, x minus a less than delta basically gives you a neighborhood of the point x, or rather the neighborhood of the point a. Okay, neighborhood of the point a. Okay, mod of x minus a less than delta basically means x is between a plus delta and a minus delta. So what is this? This is basically a neighborhood of a. Okay, so this particular definition basically implies that as you take x within the neighborhood of a is the point to which x is tending. So as you take x towards the neighborhood of a or inside the neighborhood of a, the value of fx enters the or comes into the neighborhood of L. Okay, comes into the neighborhood of L. Okay, so see here you have the definition. You can take a graphical description also here. So this is your function f. This is your function f. This is the neighborhood of a. So as x comes into the neighborhood of a, the value of the function comes inside the neighborhood of L. Clear? L plus epsilon to L minus epsilon. Got it? Clear? So this basically implies that as x comes close to a, fx comes close to L. As simple as that. Now in a similar way, we define the definition or define the multivariable limit. So what is a multivariable limit? So we say that f approaches the limit, f approaches the limit L as xy approaches to x0 y0 if the values of fxy lie arbitrarily close to fixed real number L for all xy that are sufficiently close to x0 y0. The same definition as we had used in the concepts of single variable limits, just here we have two independent variables, there we had one independent variable. Okay, and the other thing is that the path is basically the region. Here you have to take a region in the form of a disk itself. So it is not nothing very complex, very simple. If you already understand the concepts of limits of a single variable function, it is very easy to understand the concepts of a multivariable function, limit of a multivariable function. Okay, so see the delta epsilon definition. So you are given this. Okay, the limit of xy, f of xy is equals to L as xy tends to x0, y0. So for all epsilon greater than 0, there exists a delta greater than 0 such that root over of x minus x0 whole square plus root over of y minus y0 whole square is less than delta, implies f of xy minus L is less than epsilon. Now see, we know distance formula, right? What is the distance between xy and x0, y0? So this is given by the distance formula, x minus x0 whole square plus y minus y0 whole square. Now this is the thing which we have taken here. So what we are trying to say is that as the distance between xy and x0, y0 decreases, for arbitrary delta greater than 0, it is less than delta. That means as the distance between x minus x0 and y minus, as the distance between xy and x0, y0 decreases, the distance between fxy and L decreases. Clear? That is, as xy gets close to x0, y0, fxy gets close to L. Is it clear? Is it clear? Got it? Okay. Now what we can do here is that, see, xy getting close to x0, y0 means that on the x-axis x is getting close to x0, and on the y-axis y is getting close to y0. So we can define that xy is getting close to x0 as x is getting close to x0 and y is getting close to y0. That is, x is getting into the neighborhood of x0 and y is getting into the neighborhood of y0. Is it clear? Is it clear? The same thing, a point is getting close to another point means that on the x-axis it is getting close to the abscissa, and on the y-axis it is getting close to the ordinate. We did the same thing here. Xy approaching x0, y0 means that x is approaching x0 and y is approaching y0. Clear? So this is another delta epsilon definition of the multivariable limit. The properties of limits are same as that we had studied in the single variable limit. Okay, so if you take limit xy tends to x0, y0, f of xy equals to L, and limit xy tends to x0, y0, g of xy equals to M, then the limit of their summation or subtraction is equals to L plus minus M. The limit of their product is equals to the product of their limits. Limit of a constant multiple of that function is equals to constant multiple of that limit, and the limit of the division of that of their functions will be the division of their limits, provided that the denominator is not equals to 0. As simple as that. Okay. Also, if m and n are integers and fxy is taken to the power of m over n, where n is not equal to 0 obviously, and then the limit of xy is taken to x0, y0, you get the power of the limit raised to the power of m over n. Okay, provided that the limit L over n, limit to the power of m over n is a real number. Is it clear? Okay, now using the delta epsilon definition, let us find the value of a few limits. Okay, so you are given limit xy tends to 1 to limit xy tends to 1 to 2x plus y equals to 4, right? Limit xy tends to 1 to 2x plus y equals to 4. Okay, now we need to find the value, using the delta epsilon definition. Okay, very simply. Clear? Acha. Now first let us take the scratch work into consideration, then we can obviously what do we do under scratch work is that we take the final statements of the delta epsilon definition into consideration, and we take a value of the delta such that it is related to epsilon, and then we go on to our proof. I'm telling you, see, suppose you have mod of x minus 1 less than delta, and mod of x minus 1 is less than delta, and mod of y minus 2 is less than delta. Now mod of x minus 1 is less than delta implies 2 times mod of x minus 1 is less than 2 delta. That implies mod of 2x minus 2 is less than 2 delta, and mod of y minus 2 is also given less than delta. So we can say mod of 2x minus 2 plus mod of y minus 2 is less than 3 delta. That implies we can say, now see, mod of a plus b is always less than equals to mod a plus mod b, right? Now we just convert this to this form, because when we will be doing the back calculation, we will get our desired value. Okay, so if you take a plus b here, where a is 2x minus 2 and b is y minus 2, you get 2x plus y minus 4 is less than 3 delta, okay. Now if for all epsilon greater than 0 there exists a delta greater than 0, such that delta 3 delta is less than epsilon, then that implies 2x plus y minus 4 is less than epsilon. That is the definition of limit. That is when x plus y is x minus x0 is less than epsilon and y minus y0 is less than epsilon. You get the function minus the limit and their modulus is less than epsilon. So that was less than delta. Okay, this becomes less than epsilon. So this is what we have proved here. Clear? Got it. Here we don't need to do scratch work because this was a very simple problem. Okay. Here mod of a plus mod of b was replaced with mod of a plus b. Reason being, if mod of a plus mod of b is less than k, then this is also less than k. Got it? So this is also less than 3 delta. Clear? Okay. Let us check this one. Now in this case we need to do some scratch work because here the function is a little bit complex. Okay. Let's see. So for the limit of this, as xy tends to 0, 0 is equals to 0, we must have mod of xy by root over of x square plus y square minus 0 less than epsilon, which implies we need to have mod of xy upon mod of root over of x square plus y square less than epsilon. Okay. Now what is x minus y whole square? X minus y whole square is x square plus y square minus 2xy, and it is always greater than equal to 0 because x and y are real numbers. That means xy is always less than equals to x square plus y square over 2. Clear? So what we can do here is that we can convert x mod of xy to x square plus y square over 2. Just in case when we will doing the back calculation, we can replace x square plus y square over 2 by xy. Okay. So that implies to, using this particular statement, we can say x square plus y square by 2 into root over of x square plus y square is less than epsilon. So this cancels out, right? And here you have root over of x square plus y square upon 2 is less than epsilon, okay. That implies to, I'm doing the continuation here, that implies to root over of x square plus y square is less than 2 epsilon, or that implies to root over of x minus 0 whole square. So here we are taking the first statement into account, is less than 2 epsilon. Okay. Now let delta equals to 2 epsilon for all epsilon greater than 0. Okay. If we take this into consideration, then we can obviously say that for all epsilon greater than 0, there exists a delta greater than 0 by this definition, such that mod of x minus 0 whole square plus y minus 0 whole square is less than delta implies root over of x square plus y square by 2 is less than delta by 2. Okay, is less than delta by 2. Now then we will be doing the exact back calculation, right? Now see, this can be written as, I'm doing the calculation here, let's say. Now this can be written as x square plus y square upon 2 times root over of x square plus y square, which is less than delta by 2. Now from x minus y whole square, which is greater than equal to 0, we can obviously say that x square plus y square by 2 is greater than equals to xy. Okay, is greater than equals to xy, so we can put xy here, mod of xy here. Okay, we can take mod of xy here because x square plus y square is positive, right? So from here we can write that mod of, or rather we don't need to put mod initially, let us say, so we can say that xy by root over of x square plus y square is less than delta by 2. That means mod of this is less than delta by 2. We can put mod in the denominator because root over of x square plus y square is always positive, because x square and y square and the summation is always positive. Is it clear? Okay, now putting this, now from here we can say, okay, now from here we can say, I'm doing the rest of the calculation here. From here we can say mod of xy by root over of x square minus y square minus 0 is less than delta by 2, and delta was equals to 2 epsilon, right? So putting delta equals to 2 epsilon here, we get xy by root over of x square minus y square minus 0 is less than epsilon. Hence the limit of xy over root over of x square plus y square, this was x square plus y square, minus 0 is less than, hence the limit of xy over root over of x square plus y square as xy tends to 0 comma 0 is 0. Is it clear? Is it clear? Got it? In a similar way, we have further properties of limits. Okay. For example, if this is a limit you are given, we can substitute x minus x0 with r cos theta, y minus y0 with r sin theta, where r square is equals to, where basically r is the distance between x, r is the distance between xy and x0 y0. Okay, and theta is the tan inverse of y minus y0 and x minus x0. Clear? So the definition of limit can be further expressed as, for any given epsilon greater than 0, there exists a corresponding delta greater than 0, such that for all r and theta, where r is less, mod of r is less than delta, you have the function of r cos theta and r sin theta minus L less than epsilon. Okay, so basically a very similar definition, just here you are replacing x minus x0 with r cos theta and y minus y0 with r sin theta. Okay, let's see. Let's take this particular problem into consideration. So you are given the function x cube over x square plus y square. You have to prove that the limit of this function tends to 0 as xy tends to 0 comma 0. Clear? So now you take x equals to r cos theta, y equals to r sin theta, so you get r square is equals to x square plus y square. We got here x0 y0 is equals to 0 comma 0 and tan theta is equals to y over x. Is it clear? Got it? Okay. Now we will do the similar scratch work. Okay, the scratch work is that you take mod of r cos theta, r sin theta minus the provided limit less than epsilon, and continuing to do it, we just find the value of delta with respect to epsilon, and then we do the forward step. So this is basically a backward step of what we should have done to prove the limit. Okay, so you take, if r cos theta, r sin theta, it comes out to be r cos cube theta, that less than 0, because 0 is the limit you need to prove, and mod of that is less than epsilon. Okay, so that means mod of r times mod of cos cube theta is less than epsilon. Now we know cos cube theta is less than 1 always. Okay, less than equals to 1, you can say. So if we put this here, so we can say that mod of r is coming out to be less than epsilon. So what we can do is that we can take delta to be less than epsilon. We can take delta to be less than epsilon. So if delta is less than epsilon, then mod of r is less than delta, which means mod of r times mod of cos cube theta is less than epsilon, less than delta. Okay, since mod of cos cube theta is less than 1. So if it is less than delta, then mod of r times cos cube theta is less than delta, then r cube cos cube theta over r squared, and that its mod is less than delta. Okay, and this is basically your f of r cos theta, r sin theta. Okay, you can also write this as r cube cos cube theta by r square minus 0, and delta is less than epsilon, so it is less than delta means it is further less than epsilon. So this comes out to give you this particular statement. So by the delta epsilon proof, we can say that the function is, the limit of the function is 0. Is it clear? So let this lecture be up till this one, guys. In the next lecture, we will be talking about the two-path test of non-existence of limit. Okay, so meet you guys in the next lecture.